Yeah. So welcome everyone again. In this particular subject, engineering maths, our focus is mainly on 9 different topics. Okay. And the first topic which we are going to start today is linear algebra. Apart from that, we'll study calculus, basic calculus, we can say. Then vector calculus, differential equation, probability and statistics, Laplace transforms, numerical method, complex variables, and Fourier series. Okay, so it's quite um, big topic. Okay, a quite big subject, we can say. Um, sorry, yeah, I'm trying to log in through my mobile also. So whatever you will reply in chat box, I'll be able to see in my mobile. Okay, so with that introduction, we'll start the session. Just give me a minute. Yeah, I'll fix some things. Yes, yeah. Sorry for the inconvenience. So let's continue now. I'll just list down the topics first, and then we'll start the first topic. Okay. So write down heading engineering mathematics, and the name of the topics are linear algebra. First one. Second is calculus. Yeah. Second is calculus. Third one is vector calculus. Linear algebra. Then we have to study calculus, vector calculus, differential equations, probability and statistics, then Laplace transform, numerical methods, complex variables, and the Fourier series. Okay, before we jump into the first topic, linear algebra, I would like to give some brief introduction about all these topics. Okay, like what are the points which we will be going to study in those topics. Okay, um, out of this, basically 9 topics, some of the topics might be like not given in detail in your syllabus book. If you go through it, you will realize that um, they have consolidated like some of these topics together, not separately. But in short, you have like all of these chapters are important for you, and we will mostly will follow the same sequence here. Okay. In linear algebra, our focus is mainly on. So today's class is like will be mainly on theoretical understanding. Okay, so we'll try to understand whatever we have studied till now on related to the matrix, different types of matrix, properties, and all. Okay. Apart from that, in this chapter, we our focus is to understand some concepts like determinant, inverse, rank of the matrix. Okay, and at the later stage of this chapter, we will focus on solution of linear equations and eigenvalues and eigenvectors. Okay, so this is overall idea about the first topic. So we'll play around matrix only. Okay, and today's session will be more or less like very theoretical. I have some slides which are already prepared, um, so that will save our time in order to understand the theory part. Before we jump into the more difficult topics, it's good to go through some basics, and that is what we're going to do today. The another topic is calculus. You can call it as a basic calculus. The second one, and in this chapter, we will study limits. Okay, we'll understand how to. We'll understand the importance of limits. Then we'll implement that uh, to understand continuity and differentiability of the functions. Okay, so when we'll say the function is continuous, when we'll say the function is differentiable, so all those things are depend on limits. So this is what we'll study in calculus, the first part of the chapter. Then we'll study um, partial derivatives. Then we'll study different types of integrals like definite integral, improper integral, mean value theorems. Okay, multiple integrals, double and triple integrals. So this calculus topic is like one of the biggest topic um, in this subject. Okay, um, so this is what we are going to study in the second chapter. So whatever we have studied, like whatever we'll be studying in calculus, similar things we'll implement in the third chapter, that is vector calculus, but we will be dealing with the vectors. Okay, so applying derivatives and integration um, in the vector field um, gives us some relevant things, and that is what we are going to study in the third chapter, that is vector calculus. Okay, um, main, mainly we'll understand some theorems in it. Apart from that, we'll understand gradient, divergence, curl kind of concepts. Okay, so this topic is mainly related to some theorems and understanding the concept of gradient, divergence, and curl, etc. Then we'll study the differential equation, the fourth chapter. Uh, the idea of this topic is to um, solve the differential equation. Okay, so we'll not create the differential equation in this. So what are we'll be having a differential equation, and our focus will be mainly on solving the different type of differential equations. Okay, so there are variety of differential equation possible, um, single order, single degree, and then higher order differential equations, homogeneous, non-homogeneous, exact, non-exact, and so on. So we'll go into the details of that when we'll study it, but in short, our focus is on solving the differential equation and getting the solution for it. The fifth chapter is probability and statistics. The statistics part of it contains understanding the um, measure of central tendency and dispersion. Okay, measure of central tendency is like trying to achieve the central value of the data. So in like we'll study mean, median, and mode, which are measures of the central tendency. Then Measure of dispersions are like standard deviation, variance, etc. Okay, so that part we'll study in the statistics. We'll also study correlation and regression in this. Okay, um, and in probability, yeah, variety of problems we'll understand. We'll understand different types of events, uh, dependent, independent, mutually exclusive, etc., and the Bayes theorem as well. Okay, so this is the overall idea about the probability and statistics chapter. After that, we have Laplace transform. So yes, we have someone has raised hand. If you have any doubt, feel free to put your comment in chat, or you can directly ask me. Okay. Apart from that, in the next chapter, Laplace transform, we'll focus on finding the Laplace and inverse Laplace transforms. Okay, and also the application of Laplace transform in order to solve the differential equations. So that is what we are going to study here. Then we have numerical methods in this chapter. Our focus is on like studying the different numerical methods which can be used to solve the variety of problems such as algebraic equations, differential equations, or integration problem. Okay, so these kind of problems can, we know, we can solve by exact methods, or our we'll get the exact solution by um, the methods which we have. But in order to achieve the approximate answer for it, we can still use numerical methods apart from the um, traditional methods which we have. Okay, and that is what our focus will be in this chapter. The next one is complex variables. Okay, here we'll deal with the complex numbers, understanding the complex function, analyticity of the complex functions. Okay, and uh, understanding the theorems associated with it. Okay, and the last one is Fourier series. In this is very small topic, um, where we'll study how to convert, or how to convert a function into a Fourier series. Okay, how can we write a function in the series format? That is what we'll study in this. Okay, so this is very small glimpse of all chapters which we'll study throughout this subject. Okay, as I said, out of all these chapters, calculus is the biggest one, and yeah, of course, all other topics are also equally important. Yeah, till this point, anyone have any doubt before we start the first chapter? Yeah. Okay. Um, so every session will record. In case you miss any session, you can go through the recording, and after the completion of the subject, um, we will be uploading all the PPTs to one drive location, so which you can access um, as notes. Okay. Yeah. Yeah. As I move on to the topics, feel free to interrupt me in case you have not written the slides, or you have any doubt, or let's say if I'm going fast and you are still writing, you can feel free to put a message in our uh, chat box, and I will come back to that slide. Okay, but I'll make sure that after teaching each and every slide, I will ask you whether I should proceed or not. Okay, so write down heading linear algebra. Yeah, as I said, in this chapter, our focus is on understanding the matrices part, like basic theory we'll study today. Okay, hardly will touch some numericals today. Main focus will be understanding the basic concepts. Then um, we'll go through the concepts of determinant, inverse, rank, and after that, at the later stage of this chapter, our focus will be on understanding the solution of linear equations and eigenvalues and eigenvectors. Okay, I think I have already given this introduction to you. So without wasting time, we'll directly jump into the theoretical part. Okay, if you want, you can write down these things, or if you want, you can skip as well. Yeah, okay. I'll go to the next slide. Yeah, I have kept some of the slides, at least first uh, 8 to 10 slides ready, in order to make sure we save our time, and because it's just a theoretical part, and will not waste much time in writing it. Any matrix A, um, which we can write in terms of Aij m cross n. Okay, so I here represents the row number, and j here represent the column number. Okay, and m represents the number of rows, and n represents the number of column. Okay, so in short, the value of I is varying from 1 to m. What does it means? It means that in a matrix we can have 1 to m number of rows. Okay, and similarly in a matrix we can have 1 to n number of columns. So I is varying from 1 to m, and j is varying from 1 to n. Okay, so if I want to, let's say, identify any number inside this matrix, or locate any number inside this matrix, I can just use this I and j terminology. For example, if I say A22, it means that this is the element which I am focusing on, which is lying in the second row and the second column. So this is our second row. Okay, and this is our second column. Wherever it meets, that is our targeted element. Okay, so this is I hope everyone knows this. Any doubt till this? Can I proceed? Yeah, so depending on now different values of m, different values of n, there are a variety of type of the matrices, and that is what we are going to study now. So write down heading types of matrix. Write down heading type of matrix. First type of matrix is rectangular matrix. Yeah, so if number of rows and number of columns are unequal, that type of matrix we can call it as a rectangular matrix. So what is the meaning of m? M means number of rows, n means number of column. So m is not equal to n. It means your matrix will look like a rectangular shape. Okay, so for example, 2 cross 2 matrix will not be a rectangular, but 2 cross 3 or 3 cross 2, where number of rows and number of columns are different, we can call them as a rectangular. But if the number of rows and number of columns are equal, in that case we can call it as a square matrix. Okay, so the basic types are the rectangular and square matrix. if in a matrix we have just a single column, okay, so we are writing matrix A as Aij m cross 1. Okay, what does it mean? We have m number of rows but a single column. So for example, it will look like this: 1 2 3. So this is our column matrix. We have 3 rows and 1 column. So this is our column matrix. Row matrix, similarly, we have 1 row, okay, and it can have a number of columns. So if I write it like this: 1 2 3, it's a row matrix. Okay, zero matrix, you can also call it as a null matrix. We say whenever all the entries in the matrix are 0, we call it as a zero matrix. Okay, irrespective of size of matrix, if all the entries are 0, we call it as a zero matrix. Is it clear till this? Can I proceed? Yeah. Yeah, let's bring some little complexity into it now. Now our focus will be mainly on square matrix. Okay, square matrix. What is square matrix? M is equal to n. Numbers are equal to number of columns. So let us consider this 3 cross 3 matrix. So we'll have 3 rows and 3 columns. If principal diagonal elements are non-zero, okay, rest of all the elements are 0, okay, in that case you can call it as a diagonal matrix. What is the definition of the diagonal matrix? Principal diagonal elements are non-zero. If the principal diagonal elements are same, so in this first example I have written just A, B and C. A, B and C can be different numbers, but if all these principal diagonal elements are same, like either A or BBB or CCC, any particular number, in that case we can call it as a scalar matrix. Okay, what is scalar matrix? Principal diagonal elements are non-zero first of all, and they are same. So what you can write is Aij is equal to K if I is equal to J. I is equal to J in the sense we are talking about the elements 1 1, A11, A22 and A33. Okay, and whereas I is not equal to J means we are talking about the elements such as A12, A13, A21, A23, A31, A32. Okay, which should be 0. So scalar matrix is a diagonal matrix, but diagonal matrix may or may not be a scalar matrix. Are you following it? Yeah. So unit matrix is the eighth type. You can also call it as identity matrix. We all know it, and we represent it by using I, right? I stands for identity matrix. And in case of identity matrix, principal diagonal elements are 1, rest of all elements are 0. So the same thing you can use here, same logic you can write, except in place of K, the value should be 1 here. So unit matrix is a scalar matrix, but scalar matrix may or may not be a unit matrix. Okay, if value of the elements of principal diagonal are 1, then only it is a unit matrix. Otherwise it is a scalar matrix. Okay, so scalar matrix is a subtype of diagonal matrix, you can say, and the unit matrix is subtype of scalar matrix, we can say. Okay, is it clear till this? Can I proceed? Okay, Before we jump into some other types of matrix, I'll give some quick notes to you, or basically the definitions here. First definition is the trace of a matrix, and the second definition is a transpose of a matrix. The trace of matrix is nothing but the sum of elements of principal diagonal. Sum of elements of the principal diagonal. So basically, you can see it is possible. Principal diagonal, we are talking about this principal diagonal every time in diagonal matrix, in scalar matrix, unit matrix, and all. But before mentioning this, I have told you that we are talking about square matrix only. Okay, so these all terminologies are associated with a square matrix. Okay. Okay, trace of the matrix is sum of the elements of the principal diagonal. So a11 plus a22 plus a33 plus a44 plus so on, depending on the size of the matrix. So in short, summation of I is equal to 1 to n aii will give you the trace of a matrix. The next terminology which you should know is transpose of matrix. Taking transpose of matrix means interchanging the rows and columns. So if a matrix aij is there, which is m cross n, if you take a transpose of that matrix, you can write it as a transpose a raised to the power t, like this. Okay, and it will become like aji now. Okay, aji you can write here. Okay, aji, which is n cross m matrix. So for example, here let's take this example. We have a matrix A in which 3 rows and 2 columns are there. So if you take a transpose of it, you will end up with a 2 cross 3 matrix. This row, sorry, this column will become the first row, second column will become the second row. So like this, arrangement will change. Can I proceed to the next slide? These are very basic things. Feel free to interrupt me, okay, if you feel some more explanation is needed, or you are not able to understand this point. Okay. Okay, so till now we have studied some very simple type of matrices, and now let's bring some more complexity to it by these two new types, which is symmetric matrix and skew symmetric matrix. Okay, idea behind studying transpose before this topic is because this type is depend on the, if the transpose of the matrix is equal to the matrix itself, we call it as a symmetric matrix. And if a transpose of the matrix is equal to negative of the matrix, okay, minus times matrix, then you call it as a skew symmetric matrix. Okay, I'll repeat. If A is equal to A transpose, then that is a symmetric matrix. But if A transpose equal to minus A, you can call it as a skew symmetric matrix. So we have an example here for the symmetric matrix. You can clearly see here the basic idea about the symmetric matrix is aij is equal to aji. Okay, so for example, one a12 equal to a21. Okay, complementary terms are there, they are same. So here we have 7, here also we have 7, here we have 3, here also we have 3. So like a13 is equal to a31, a23 is equal to a32, right? So 6 is here, 6 is also here, because after taking a transpose, our principal diagonal terms are not changing. Okay, only the other terms are interchanging. So that's why we can call it as a symmetric matrix. So in order to achieve this, can you tell me like what is the requirement of symmetric matrix? Can a rectangular matrix be a symmetric matrix? No, right? Because it's not possible. Because we know if you take a transpose, number of rows will interchange with the number of columns. So it should be a square matrix first of all. Okay. So the requirement is it must be a square matrix. And then if Aij is equal to Aji, then only that matrix is called as symmetric matrix. Will there be any restriction on the principal diagonal terms in case of symmetric matrix? No, right? There is no restriction. But if I talk about the skew symmetric matrix, what should be the value of principal diagonal elements? Yeah, it should be 0. Why? Because we are multiplying that matrix with a negative sign. So when we call a matrix as skew symmetric matrix, if A transpose equal to minus A, okay. So basically we can write skew symmetric matrix as Aij is equal to minus Aji. So these complementary terms are of opposite sign. So this is minus 2, this is 2, this is minus 3, this is 3, this is 4, this is minus 4. So they have a different sign. So if I take a transpose of it, how it will look like? It will look like this. Okay. Like this it will look 0 minus 2 minus 3, 2 0 4, 3 minus 4 and 0. Right? Are they identical? No. But if I multiply A with a minus 1, are they same? Yes, they'll become same. But in place of diagonal elements, if I put some other numbers apart from 0, if I put let's say 1, minus 3, 8, something like this, after multiplying by negative sign, the sign of those numbers will change, and we cannot prove that A transpose equal to minus A in that case. Okay, so apart from the requirement of a square matrix, the principal diagonal elements has to be 0 in order to achieve the skew symmetric matrix. Okay, so basic things are it should be a square matrix, principal diagonal elements are should be 0, and Aij is equal to minus Aji. Then that matrix is called as a skew symmetric matrix. Is it clear till this? Yeah, can I proceed? Okay, so let's talk about some of the properties of symmetric and skew symmetric matrix. You know now what is symmetric matrix and what is skew symmetric matrix. If A is a square matrix of order n, okay, if you take a square matrix A which is of order n, maybe 2 cross 2 or 3 cross 3, then A plus A transpose is symmetric. A plus A transpose is symmetric. Okay, write down this property. So for example, 1 2 3 4, if this is your A, if you take A transpose, what will happen? 1 3 2 4. Okay, if you add it, what will happen? 2 5 5 8. Is it a symmetric matrix? Yes, right. So you can say that A plus A transpose is a symmetric matrix. Why it is coming? Because only these two things are getting interchanged and they will get added with each other. So ultimately, you will get the same number with the at the conjugate positions. Okay, you can say like A12, A21, A13, A31. So at these positions, we'll get the same number. That is why if you take, let's say, a matrix and add the transpose to it, you'll end up with a symmetric matrix. Similarly, if you subtract the transpose of that matrix from the original matrix, you'll end up with a skew symmetric matrix. Okay, so in this case, if I just subtract here rather than adding it, you will realize that you will get the principal diagonal elements as 0. 1 minus 1 is 0, 4 minus 4 is 0, and 3 minus 2 is 1, and 2 minus 3 is minus 1. So it is satisfying what we are studying. That is, principal diagonal elements are 0 and aij is equal to minus aji. Yeah, so that is why it is a skew symmetric matrix. So now if I add this, so if I divide this matrix, let's say, with 2, and this matrix divided by 2, okay, and if I add them, I'll end up with a matrix A itself, right? Or if you just add them, A plus A transpose plus A minus A transpose, A transpose will get cancelled. You'll end up with a 2A, right? And if you divide it with 2, you will end up with A matrix. So ultimately, what I'm trying to explain through this is, if you add a symmetric matrix, okay, which is A plus A transpose divided by 2, and A minus A transpose divided by 2, which is skew symmetric matrix, you'll end up with a matrix A. So indirectly, what we can say is, any matrix or any square matrix of order 1 can be represented as sum of symmetric and skew symmetric matrix, where that symmetric matrix is A plus A transpose divided by 2, and the skew symmetric matrix is A minus A transpose divided by 2. Is it clear? The point number 3. Yeah. Similarly, if you multiply A with A transpose, you will end up with a symmetric matrix. Okay, so these are some basic properties. Can I proceed to the next slide? Okay. Yep. So now let's try to deal with two matrix. Okay. So previously we were talking about only matrix A. Now bring one more matrix B to the table. Okay. So A and B are the symmetric matrix. Then AB plus BA is also symmetric. Okay. You can try it out in your free time, like how I have shown here, like this. You can take any random example and try it. Okay. And if you still find it difficult, feel free to reach out to me. Okay. At the end of the session, I'll give my number to you. Either you can, in case of any doubts, you can reach to me. If it is a conceptual doubt, you are free to reach to me. Okay. Um, if it is, let's say, if you are facing any issue in particular problem, I would suggest you first put it in our WhatsApp group. I'm pretty sure that um, the rest of the students in the class, or any of the student in the class, will be able to solve it. And in case you still didn't get answer, I'll help you with that. Okay. Yeah. Or let me just give my number now itself. Yeah. Yeah. Coming towards this properties, if A and B are the symmetric matrix, then AB plus BA is a symmetric. AB minus BA is skew symmetric. AB is symmetric only when AB is equal to BA. What is the meaning of it? You know that A to B is not always equal to B into A, right? If it is the same, In that case, AB is a symmetric matrix. That is what we should know. Okay, this is only possible when this multiplication ends up as a symmetric matrix. If A and B are the symmetric matrix, then B transpose AB is symmetric. Okay, only when A is a symmetric matrix. Okay, I'll repeat. B transpose AB is symmetric only when A is symmetric. B transpose AB is skew symmetric only when A is skew symmetric. Okay. Um, I'll repeat. B transpose AB is skew symmetric only when A is symmetric. A is skew symmetric. Idea behind giving you these things is, if you know these properties, it will be very easy for you to save your time in during exam. You can directly take it. Okay. I would suggest you um, to go through these properties. If you feel like doubtful, you can try any random question, and you will get confidence with it. So yeah, but these are the standard properties which you should know. um, I suggest you to remember this, so in case a 1 mark question comes related to these properties, you will be able to solve it quickly. Okay? Yeah, if A is symmetric, A to the power n is symmetric. Okay, any power of A is symmetric if A is symmetric. So A square, A cube, A to the power 4, all are symmetric because A is symmetric. But if A is skew symmetric, in that case, the higher powers of A can either be symmetric or skew symmetric, depending on the power. If power is even, if n is even, like A square, A to the power 4, and so on, then you'll end up with a symmetric matrix. Okay, but if the power is odd, like A cube, A raised to the power 5, you'll end up with a skew symmetric matrix. Okay? Write down this properties. I'll just repeat the last two properties once again. If A is symmetric, any power of A is symmetric. If A is skew symmetric, even powers are symmetric, whereas the odd powers are skew symmetric. Okay, clear? Then can I proceed? Have you written this notes? Okay. Feel free to interrupt me in case you want me to stay on that slide for some more time. Okay. Yeah. So we understood the part of symmetry and skew symmetric matrix. Okay. Another term I would like to introduce at this point is conjugate of a matrix. Okay. So we understood the transpose, which was creating two types of matrix, that is symmetric and skew symmetric. So now we'll study the conjugate of matrix. Okay, which will also create new type of matrices. Okay, so let's try to understand this point first. You know conjugate numbers in complex. Okay, like uh, if z is a complex number, okay, I'll highlight here. If z is a complex number, then which is x plus iy, then its complex conjugate is x minus iy, right? So these complex conjugates we generally write as x plus or minus iy, like this. So Z, which is x plus iy, is a complex conjugate of x minus iy, and x minus iy is a complex conjugate of x plus iy. Okay, so we can write it by Z and Z bar respectively. So if I take any random example, 2 plus 3i, if Z is equal to 2 plus 3i, then the complex conjugate of it is Z bar. We have to write it as Z bar, which is equal to 2 minus 3i. Okay, so same approach we will follow in the matrix. So in case in a given matrix A, if the elements are complex, so for example, here we have matrix A in which we have first element which is I plus 1, second element is I, third element is minus 3 minus I, and the last element is 5. Okay, so in this case, if I take a transpose of, sorry, if I take a conjugate of this matrix, it means each and every complex number existing in this matrix has to be uh, conjugated. Okay, so for example, I plus 1, you can also write it as 1 plus I, which should be written as 1 minus I. Okay, so like this I will change to minus I. Minus 3 minus I will change to minus 3 plus I. I will remain as it is because 5 is a real number. You are not the meaning of 5, you can still write it as 5 plus 0i, right? You can write it as 5 minus 0i, but it is not giving any significance, so you can remove it, right? So basically, wherever the complex number is there, in order to take the conjugate of matrix, you have to take the conjugate of that individual element of the matrix. Okay, is it clear till this? So first thing is transpose, which we have studied, and second thing now what we have studied is a conjugate. Okay, so we write conjugate by bar. If matrix is A, the conjugate of that matrix is A bar. And how we write the transpose? A raised to the power T, right? A raised to the power T, like this. Now, if you take transpose as well as conjugate, okay, so like this, A transpose conjugate or A conjugate transpose, ultimately you'll get the same answer. Okay, it irrespective of sequence, whether you are taking conjugate first and taking transpose or taking transpose and then writing conjugate, nothing will change, right? Because we are dealing with the individual terms here. So um, the conjugate of a transpose of a matrix or transpose of the conjugate of a matrix of A can be written as A raised to the power theta. Okay, rather than writing like this, A to the A transpose bar or A bar transpose, we can also write it as A to the power theta. Okay, and you already know like that A to the A transpose, again if you take transpose you will get the original matrix. Similarly, if A, if you take a conjugate of it and if you take again conjugate of it, you will get the original matrix A. In the same way, A to the power theta will also give you the A, right? Similarly, A plus B raised to the power theta is A raised to the power theta plus B raised to the power theta. Okay, and K theta is equal to K bar A raised to the power theta. Okay, where K is a multiplier. It can be either real or complex multiplier. Okay, is it clear till this? Can I proceed? Just new term new term I have introduced here, that is conjugate, and which is z bar, right? Sorry, which is a bar, in which you will write the um, conjugate of individual term, and another terminology is a raised for theta. It can be written for conjugate of a transpose of a matrix or transpose of a conjugate of a matrix. Okay. I hope it's clear. Yeah. Coming towards the next slide. If now you know a theta, okay, I'll not repeat it. So if a theta is equal to a, then you can call it as a Hermitian matrix, right? Okay, so this is a new type of a matrix, Hermitian matrix. So it's more or less similar to the symmetric matrix, right? What is the definition of symmetric matrix? A transpose equal to A. But here what we are saying, A raised power theta is equal to A. A to the power theta means what? Transpose of a conjugate of matrix or conjugate of a transpose of matrix, right? So if A to the power theta is equal to A, that is there, then that type of matrix is called as Hermitian matrix. If A to the power theta is equal to the minus A, you can call it as a skew Hermitian matrix. Okay. So let's take a simple example. Take this matrix A, 1, 1 plus I, 1 minus I, 7, 6, minus I, 6 and 8. If I take a transpose of it, what I'll get? You have to replace individual row with a column. So first row will become first column, second row will become second column, third row will become third column. So you'll get A transpose like this. And now if you take a conjugate of it, every complex term will be replaced by its conjugate. Okay, so 1 minus I will be replaced by 1 plus I, minus I will be replaced with I, 1 plus I will replace with a 1 minus I. Okay, it will be replaced with a minus I. So this is what you are going to get. Okay, so here you are taking conjugate, and here you are taking transpose. Clear? Now check whether the initial matrix A and the final matrix A theta, are they same or not? Yes, they are same. So that is why we can call this matrix A is a Hermitian matrix. Okay. Any doubt here? Yeah. Okay. Let me ask you some questions here. Will there be any restriction on the diagonal terms? Will there be any restriction on the diagonal terms? No, Arjun. See, in this example, diagonal terms are not 0. I have written 1, 7, 8, right? These are not, they are non-zero. Still, it is a symmetric, still, it is a Hermitian matrix. Yeah, okay. Yeah, you are correct. For skew Hermitian, it's there. I'm talking about the Hermitian matrix now. Will there be any restriction? We are talking about the Hermitian matrix. Will there be any restriction? What will happen if I have the complex number along the diagonal? What will happen? Let's say first element is here 1 plus I. Okay. So if you take a transpose of it, 1 plus I will remain 1 plus I. And after that, if you take conjugate, it will become 1 minus I. Then are they same? No, right? So uh, can I say like the principal diagonal elements should be real? Yeah, yes, we can say like this. Okay, and one more sentence I would like to say is every real Hermitian matrix is a symmetric matrix. Can I say it like this? Because when we talk about the real Hermitian matrix means what is Hermitian? Hermitian in the Hermitian matrix, A raised power theta is equal to A, right? And in theta, what we are doing? We are taking A transpose conjugate or A conjugate transpose. If matrix is real, then there is no significance of conjugate, right? So it is same as saying A transpose. Okay, for real matrix, A raised to the power theta is equal to A transpose itself, right? Do you agree? Because conjugate doesn't make any sense in that. So it is correct if we say it like this, like every real Hermitian matrix is a symmetric matrix. Okay. Yeah. Can I proceed to the next slide? Any doubt till this? If you have any doubt, feel free to ask. Okay, I'll go to the next slide. Let's talk about the skew Hermitian matrix. If a to the power theta is equal to minus a, in that case we call it as a skew Hermitian matrix. And as you said, Arjun, yeah, here the restriction is the principal diagonal element should be 0. Okay, so we'll have same restriction here about the principal diagonal elements. Okay, so let's take an example here, which is 0, 1 plus I minus of 1 minus I, 0, 6, I minus 6, 0. Okay, so if you take a transpose of it, the number of rows will become number of columns. First row will become first column, second row will become second column, third row will become third column. Okay, so here you are taking transpose. If you take a conjugate of it, every complex term will be replaced by its complex conjugate. So for example, 1 plus I will be replaced with 1 minus I will be replaced with a minus I, and so on. Okay, and ultimately this is what your A raised to the power theta matrix. Whether it's same as original matrix? No. Whether it is equal to minus times original matrix? Yes, right? Because here it's minus 6, here it's minus I, and we can clearly see all the terms are multiplied with a minus, then we'll get the original matrix. Okay, so A to the power theta equal to minus A, and that's why this particular matrix is a skew Hermitian matrix. If I replace any diagonal term with any other number, okay, maybe for example, if I write any real number or any complex number along the principal diagonal element, in that case also you will clearly see that there is no chance to create the skew Hermitian matrix. Okay, so in order to achieve the skew Hermitian matrix, the principal diagonal elements has to be 0. Okay, and as we have studied before, every skew Hermitian matrix or every real skew Hermitian matrix, okay, write down term here, every real skew Hermitian matrix is a skew symmetric matrix. Clear till this? Can I proceed? Hello? Yeah, okay. Yeah, Further, we have some more type of matrices. Okay, so this list is going on. Lower triangular and upper triangular matrix. Okay, so yeah, that's why previously itself at the beginning itself I told you this session will be very theoretical one. Okay, but it's important. It's important to recall whatever we have studied till now in the 11th, 12th, or during first and second year of engineering, where we mainly have this matrix in our syllabus. Okay, it's been a while we studied this, so it's important to recall those basic concepts in order to study some advanced topics like solution of linear equations, eigenvalues, eigenvectors, etc. Okay, the next type is lower triangular matrix.
Hello, sir.
Yes,
Sir, in skew Hermitian matrix, principal diagonals elements may be imaginary, na, sir?
yeah, let's try it. Okay,
Yes, sir.
yeah, if I write here I, what will happen? If I take a transpose, it will remain like this, and I will be replaced with a minus I. Yes, so yeah, it is possible. Okay, so you can multiply with a uh,
Imaginary.
minus sign and you will get. Okay, so yeah, principal diagonals can either be imaginary or zero, you can say. Yeah, but the real part should be zero. Okay, but this statement is still valid. Every real Hermitian matrix is a skew Hermitian matrix. Okay, so here I'll just add AI can be zero or imaginary. Okay, yeah, thanks for highlighting it. Okay, coming towards the next um, type, lower triangular matrix. If the elements of the lower triangular part of the matrix are non-zero, okay, or the elements below the principal diagonal, including the principal diagonal, are non-zero, then you can call it as a lower triangular matrix. Okay, but what is strictly lower triangular matrix? If elements below the principal diagonal elements are non-zero and rest of all the elements are zero, then we call it as a strictly lower triangular matrix. Okay, I will repeat. If the elements inside the matrix below the principal diagonal elements are non-zero and all other elements are zero, in that case we call it as a strictly lower triangular matrix. Whereas the elements in the matrix along the principal diagonal and below the principal diagonal are non-zero, and rest of the elements which are in the upper triangle are zero, in that case you can call it as a lower triangular matrix. Okay, and opposites are the definitions for the upper triangular matrix. Okay, here we can clearly see the upper triangle is non-zero, and similarly you can have a strictly upper triangular matrix. Okay, similarly we can have a strictly upper triangular matrix. Yeah, can I proceed to the next slide? Hello, can I proceed to the next slide? Okay, just a minute. Yes. Okay. So that's all we have for theoretical points, okay, to be studied. Now, let's use this theory in order to understand some other topics in this chapter, such as determinants, okay, such as determinants um, and rank, inverse, etc. Okay, so write down heading determinant of matrix. Determinants. Okay, so understanding determinant is very important, okay, and you will see the importance of it when we study the upcoming topics, okay. If we know the determinant, on that basis we can tell about the, let's say, if you are writing matrix in the form of or if you are writing um, linear equations in the matrix form, by calculating the determinant we can judge about the solutions of the those linear equations, okay. So use of determinant is like very important in judging the type of solution which we'll get in the linear system of equations. We can also use determinant in order to um, find the inverse of a matrix and um, finding the eigenvalues and eigenvectors, okay. Eigenvalues, eigenvectors, you know, like have very important role in a real world applications such as like frequency um, analysis, natural, in order to calculate the natural frequencies and mode shapes. Um, you might have studied eigenvalues and eigenvectors during your engineering, okay. And so the concept of this determinant will also help us in that, okay. So let's start in way to how can we find the determinant of matrix, okay. So if it is a simple 2 cross 2 2 cross 2 matrix, any matrix A, B, C, D in general, then the determinant of a matrix is represented like this: mod of A, and it will, the value of that will be equal to A D minus BC, multiplication of A into D minus BC, okay. But if it is a 3 cross 3 matrix and so on, then things will become little complicated, okay. A11, or sorry, A1, B1, C1, A2, B2, C2, A3, B3, C3, okay. Before we jump into the way to calculate the determinant for it, we should understand some more concepts such as minor and cofactor, okay. So minor of any element, let's say for example minor of B1 is what, except that element, like that row and column corresponding to that element, okay. Whichever terms are there, if you write into the determinant format, which are A2, C2, A3 and C3, then that is called as a minor of B1, okay. What is minor of B1 now? A2 C3 minus C2 A3, right? A2C3 minus C2A3. That is called as a minor of B1. So in the same way, we can calculate the minor of any term. So how the minor of A1 will look like? Determinant of B2 C2 B3 C3. So it's a B2 C3 minus C2 B3. Okay. So like this, we can calculate minor of any term or any element. Another definition which you should know is cofactor. Cofactor of any element Aij in general is equal to minus 1 times I plus j multiply by minor of Aij. Okay. Cofactor of Aij is equal to minus 1 raised to the power I plus j into minor of Aij. Okay. So for example, what is cofactor of let's say this B1 term? Cofactor of B1 will be equal to minus 1 raised to the power first row and second element column, right? So it is 1 plus 2 into minor of B1 we already calculated, A2C3 minus C2A3, right? Like this. Okay. So I hope you understood how to calculate minor and cofactor. So this terminology is used in order to find the determinant of the matrix. So determinant of matrix A, which is 3 cross 3. I'll repeat again here: A1, B1, C1, A2, B2, C2, A3, A3, C3. Okay, then determinant of this matrix A is small a1 multiplied by capital A1. Capital A1 is like a um, cofactor of small a1. Okay, so the cofactor of B1 we generally write it by capital B1. Similarly, cofactor of A1 is written as capital A1. Okay, so I hope you understood this nomenclature: A1 capital A1 plus B1 capital B1 plus C1 capital C1. Okay, in the same way, A2 capital A2 plus B2 capital B2 plus C2 capital C2. Either row wise or column wise, you can write it like this. Okay, so in this way, so these are the different ways to calculate the determinant of the matrix. Okay. Yeah. Is it clear to everyone? So in general, how you write directly you. So this is what you do, but how you write it? Let's say in general, A1 to B2 C3 minus C2 B3 minus B1 time A2 C3 minus C2 A3 plus C1 times A2 B3 minus B2 A3, right? Like this you write, correct? So this is capital A1, this is capital B1, this is capital C1. So on you can write, okay, by other ways. If you consider second row or third row and so on. I hope it's clear till this. Yep. There is one alternative method which we have is Sarah's rule. Sarah's rule, which is applicable for 3x3 matrix. This also you can use if you find it easy, but yeah, if you are following the traditional method, that is well and good. This is just for your information as an optional method. So we have 150 minus 1 2 4 0 1 and 3. Okay, if we are supposed to calculate the determinant of the matrix, how we calculate? 1 times 2 multiplied by 3 is 6, minus 4 multiplied by 1 minus 5 times minus 1 multiplied by 3 is minus 3, 0 multiplied by 4 is 0, and then we have plus 0 into anything. Okay, 0 into minus 1 minus 0. Okay, so if you solve it, 6 minus 1 is 5, 5 into 1 is 5. Sorry, this is 4. Okay, 6 minus 4 is 2 plus 15 plus 0, it is 17. Okay, you will write it like this. But in Sarah's rule, what you do? So this is our traditional method, right? This is our normal method. In Sarah's rule, what we can do is uh, the way it works is you have to rewrite the terms of the first and second column again. 1 minus 1 0 5 2 and 1. Okay, and then you are supposed to draw the inclined straight lines. Okay, mm. So let's name it as first line, second line, third line, fourth line, fifth line, and sixth line. Okay, like this. And then see, this is I'm explaining to you, but in a exam or during your whenever you're solving it or practicing it, no need to draw these kind of lines. Okay, straightforward, you can just do these calculations in your mind. So what we are doing is we are multiplying along these lines and adding them, and then subtracting with the another slope. So here first, second, and third line. What is the multiplication of first line? First line is 6, second line is 0, third line is 0. Okay, so 6 plus 0 plus 0 minus, what is the multiplication of fourth line? 0. What is the multiplication of fifth line? 4. What is the multiplication of sixth line? Minus 15. Okay, so minus 15 plus 4 is minus 11. Minus multiply minus will become plus. So 6 plus 11 will end up with again 17. Okay, so you will get the same answer. So you can do these calculations in mind also, and more or less similar time it will take. Okay, so whichever method you feel easy, you can use it. Okay, is it clear till? Can I proceed to the next slide? Okay, write down heading properties of determinants. write down heading properties of determinants. Okay, so if we have the first property is, if you have matrix AB, then multiplication of AB, if you take a determinant, you will end up with determinant of A multiplied by determinant of B. Second property, determinant of A transpose is equal to the determinant of A itself. Okay, so let me just give you one example here. Let's take a matrix A, which is 1, 2, 3, 4. Take a transpose of it, 1, 3, 2, 4. Okay, so determinant, what you are doing, 4 minus 6, 4 minus 6. Okay, and you will end up with a minus 2 and minus 2 respectively. Okay, um, so in short, what we can say here is only the, so apart from principal diagonal term, rest of the terms which are complementary terms, okay, right, a1 2 or a2 1, or in 3 by 3 matrix, a1 3, a3 1, a2 3, a3 2, so on, they will interchange. So ultimately your multiplication is going to remain same, and hence your determinant is um, same. Okay, is it clear? Yeah, we got one question here from Jagdish. Can we find determinant of 4 by 4? Yes, we can find it. Okay, but I don't expect like they'll ask any questions on it. Okay, yeah, but yeah, in short, like determinant we can find for um, let's say higher order matrix as well, not just 4 by 4, 5 by 5 matrix and so on. Also, we can find. Okay, is it clear? So either it can be 0 or non-zero. Yeah. From exam point of view, I would expect like they'll ask you hardly 2 cross 2 or 3 cross 3. If we go in higher order derivatives, sorry, higher order matrices, calculating the determinants will take time, and I don't expect they'll ask this in exam. Okay, considering the time available to solve each question, you may get 4 cross 4 or 5 cross 5 matrices in the rank topic, okay, where we have to find the rank of the matrix, but not in the determinants. Yeah, but yeah, in short, we can find the determinant for higher order matrix as well. Okay, coming towards this properties of determinant, the determinant of A transpose equal to determinant of A is our second property. Coming towards the third property, if you interchange the rows, okay, so for example, ith row if you are interchanging with a jth row, or if you are interchanging the column, ith column, if you are interchanging with the jth column, what will happen? Can anyone tell me? What will happen?
-1. -1 we have to multiply.
Yes, correct. So basically sign changes. Okay. So if it is if determinant is negative, it will become positive. If it is positive, it will become a negative. So let's take same example. A matrix is 1, 2, 3, 4, and you are interchanging the rows. So 3, 4, 1, 2, you are writing it like this. You know, determinant of it is -2. Now calculate the determinant for it. You will get it as 2. So basically, sign is changing if you interchange the row. Similarly, you can try for interchanging the columns. You'll end up with the same answer. Okay. So if I interchange the column 2, 4, 1, 3, I'll give you the 2. Okay. So this is the column and this is for row interchange. So the next property, can I proceed to the next slide? Next property, determinant of Ka is equal to K raised to the power n determinant of A. Okay, so K is here is scalar, you can say. Okay, for example, you know a matrix A, same matrix will take 1, 2, 3, 4. What is it? What was the determinant? -2, right? So now if I write phi A here, what is how the phi A will look like? 5, 10, 15, 20. Okay, and if I take a determinant of this phi A, how it will look like? 5 into 20 minus, so which is 100, minus 150, it is -50. Okay, so rather than writing like this, can I directly say determinant of phi A is equal to, if I know the determinant of A, so it is 5 square into -2, which is equal to -50. Directly I can write because I know the determinant of A. Okay, so that is 2 here, 2 is here. Order of the matrix, it's a 2 cross 2 matrix, so it can be n cross n matrix. That's why in general we are writing K raised to the power n determinant of A. Clear? Can I proceed to the next slide? Yeah, we have some space here, we can write if A is, or if A contains 0 elements in a row, or all elements are 0 in a row. If all elements are 0 in a row or a column basically of matrix A, then what is the determinant of it?
0.
Yeah. Okay. If all the elements are 0 in a row or column of a matrix, then the determinant also 0. The next property is, let me just go to the next slide. If I am performing row operation, okay, so ith row, if I am modifying it as, let's say, ith row plus k times jth row, like this, or if I am performing column operation, okay, ith column I am writing as, let's say, ith column plus k times jth column. Okay, in short, I am performing row or column operation. How it will affect the determinant? Can you tell me? After performing row operation or column operation, what will happen to determinant?
I guess we will get negative values, sir.
No. Determinant will remain same because um, here we are not, let's say, interchanging anything. Okay, if you interchange anything, in that case what will happen, the sign will change, because let's say the bigger number was on left hand side of the subtraction will now come to the right hand side of the subtraction, and that's why the sign, let's say, will change. But in this case that is not going to happen. Let's take example. So it will remain same basically. 1 2 3 4. Okay, determinant is -2, we know. So now let's say I'm performing an operation r1. I'm writing as r1 plus 3 times r2. What is going to happen? It will become like 3 times 3 plus 1 is 10, 4 times 3 plus 2 is 14, 3 and 4. Okay, what will happen? 10 into 4 is 40, minus 14 into 3 is 42. Still you'll end up with a -2 answer. Okay, so ultimately what we can say is, here if you perform the row operation or the column operation, it will not affect the determinant. Okay, so that's why you can see, like whenever you are calculating the or whenever you are solving the equations, we perform row operations, right? Because we know after performing operation, determinant will not change, and because determinant will be unique for that um, matrix, and it will tell us what kind of solution we'll get from those set of equations. Okay, clear? The next property, if two or more identical elements, sorry, identical rows are there or columns are there, what will happen to the determinant?
Zero. Zero.
Yes, correct. It's 0. Why? Because you can perform row operation or column operation, and you can easily make that row or column as 0. And if a single row or column, even if we have a single row or column which is entirely 0, in that case we'll have determinant as 0. Okay. Yes. One more point I would like to introduce, or a note. Can you tell me what is determinant of skew symmetric matrix of order, of odd order? I'll repeat. Determinant of skew symmetric matrix of odd order.
Zero.
Yeah, correct. It's 0. Odd order in the sense 3 cross 3 or 5 cross 5 order. What is the definition of a for a skew symmetric matrix? A transpose equal to minus A. Correct. Then only we'll say the matrix is skew symmetric. If we take a determinant on both the side, determinant of A transpose equal to determinant of minus A. We have already studied that determinant of A transpose is equal to determinant of A, right? And you can still write it as -1 times determinant of A. Do you agree? And so it's like a Ka, and you know how to treat it. We can write it as minus raised to the power n times determinant of A. Suppose if n is odd, what will happen? Determinant of A is equal to -1 raised to the power n determinant of A. You can, this minus, this will become -1, right? Correct. If n is odd, you will get it like this. If n is even, Determinant of A equal to determinant of A you will get. Okay. So basically you will not be able to you will not judge, you will not be able to judge about the determinant. You have to calculate it if n is even. When is odd, what we are getting here, you are getting determinant of A is equal to determinant of minus A. Sorry, minus times determinant of A. And when it is possible when only when the value of determinant itself is 0. Do you agree? If value is 0, then it's a plus 0 or minus 0 doesn't make any sense. So um, that's why um, it is correct if we say determinant of a skew symmetric matrix of odd order is 0. I hope it's clear. Another note, if any two rows or columns are proportional, okay, then determinant of that matrix will be what?
0.
Yeah, correct. Again 0, because if they are proportional, then we can make them 0 by performing row or column operation. Yeah. Okay. Yeah. So I think this is uh, enough introduction. Some standard results I'll give to you, which you should know, or in case in exam if they ask, you will be able to quickly answer it. Okay. Let me just give some simple results like 1, 2, 3, 4, 5, 6, 7, 8, 9. Can you tell me the determinant here? 0. Correct. Why? Because if you perform the row operations, this is your row number 1, row number 2, row number 3. The difference here in the first versus second row and the second versus third row is same, right? And then you can make them as a proportional rows, right? So, or basically you can get the rows which are mm, identical. So for example, if I perform the operation R2 is equal to R2 minus R1 and R3 is equal to R3 minus R1, we know after performing row operation or column operation, determinant won't change. So 1, 2, 3, 3, 3, 3, and then R3 minus R2 also you can do. Okay, so it is 3, 3, 3. So these two are these two are identical. So you can make it 0 and determinant will be equal to 0. Okay, some standard results I'll give you. Okay, just note it down. 1 plus A, 1, 1, 1, 1 plus B, 1, 1, 1, 1 plus C. A, B, C, in bracket 1 plus 1 upon A, plus 1 upon B, plus 1 upon C. 1 plus A, 1, 1, 1, 1, 1 plus B, 1, 1, 1, 1, 1 plus C, 1, 1, 1, 1, 1 plus D. A, B, C, D. 1 plus 1 upon A, plus 1 upon B, plus 1 upon C, plus 1 upon D. Okay. Let me give you some more standard results on the next slide. Can I proceed to the next slide? 1 1 1 A B C A square B square C square, or 1 1 1 A B C A square B square C square, because they are like transpose of each other. Okay, in this case you can write it as A minus B, B minus C, C minus A. Okay, A minus B, B minus C, and C minus A. 1 1 1 A B C A cube B cube C cube A cube B cube C cube. Just a minute. Or 1 1 1 A B C A cube B cube C cube. You can write it as A minus B, B minus C, C minus A times A plus B plus C. Okay. Um, yeah, and the last standard result, write it down, 1 1 1. So just go through it, because if in case they ask in exam, uh, you um, you know the solution. Okay, it will save your time. Minus B, B minus C, C minus A times AB plus BC plus C. Okay, yeah. So basically, from the determinants point of view, what I would expect is you should have clear understanding about how to calculate the determinant, mainly for 2 cross 2 and 3 cross 3, and the properties of the determinant should be clear. Okay, how the things like interchanging the rows or columns, performing the row or column operations, okay, will affect the determinant. That is also a very important point. Okay, is it clear? Can I proceed to the next slide? Yeah. Okay. Um, Next point which we will going to study is inverse of matrix. Okay. Um, Inverse of a matrix is given by 1 upon determinant of A. As I previously said, determinant will help us to calculate the inverse of a matrix. Okay. 1 upon determinant of A, adjoint of A. So new term we are introducing now here, which is adjoint of A. Okay. So before jumping into the adjoint of A, um, from this equation, what we have and we can understand is the determinant, if it is equal to 0, then A inverse doesn't exist. Okay? And that type of matrix is called as singular matrix. Okay? So singular matrix is the one where we have determinant equal to 0. So um, Determinant 0 means it's a singular matrix. Inverse can't be found. And if determinant is not equal to 0, it's a non-singular matrix. Okay, inverse exists. Can you tell me what is orthogonal matrix?
A transpose is equal to A inverse.
Yes, correct. Okay, so people often confuse in between a singular, orthogonal and all. So you should know clearly A transpose, if it is equal to A inverse, then it is an orthogonal matrix. So or in other words, you can say it as A into A transpose equal to I, or A transpose into A equal to I. Okay, so both the things are same. Okay, so in the inverse part, we already know the determinant part. Okay, in order to calculate the inverse, we know first you should to find the determinant, and the second thing is to calculate the adjoint. So let's find how to calculate the adjoint of A. I'll go to the next slide. Adjoint of A is equal to cofactor matrix of A and then take a transpose of it. Okay, I'll give just small introduction. Suppose if your matrix is A, what are the elements? Let's say A1, B1, C1, A2, B2, C2, A3, B3, C3. You already know what is minor and cofactor. Okay, suppose the cofactor matrix of this is, what is the cofactor of small a1? It is capital A1. Small b1, capital B1. Okay, C1, so on. A2, B2, C2, A3, B3, C3. Okay, so I will calculate A1 minus 1 rest to the power 1 plus 1, B2, C3 minus C2, B3. Okay, like this, all the elements you will find and put in the matrix format, and then take a transpose of it. Take transpose. Okay, so it is A1, A2, A3, B1, B2, B3, C1, C2, and C3. Okay, this particular matrix is called as a adjoint of A. So if you divide the adjoint of the matrix with the determinant, you will get the inverse. Okay, what is adjoint of zero matrix?
0.
Yes. What is adjoint of identity matrix?
Identity, sir.
Yes, correct. Identity matrix itself. Okay, this also you should know. What is adjoint of matrix A into B? It's adjoint
Adjoint
of
of B
B.
and adjoint of A.
Perfect. Okay, so these are some of the properties of the adjoint which you should know. Okay, please let me know once you are done with this slide. Adjoint of Ka is equal to k raised to the power n minus 1 adjoint of A. Okay, read out this point where k is the scalar and n is the order of the matrix A, then adjoint of k is equal to k raised to the power n minus 1 adjoint of A. The next property, determinant of adjoint of A is equal to determinant of A raised to the power n minus 1. Let me write it on the next page, make it clear. Determinant of adjoint of A is equal to determinant of A raised to the power n minus 1. Determinant of adjoint of A is equal to determinant of A raised to the power n minus 1 into n minus 1. Okay, so basically determinant of A raised to the power n minus 1 whole square. So on you can write. Okay, so these are some of the properties of that joint. So if I give you a simple example of a 2 cross 2 matrix, let's say a matrix A, B, C, D, how the inverse will look like? Inverse will be equal to 1 upon determinant, which is equal to AD minus BC, and into, yes, DA it will become, and this will be minus B. That's all. Okay, directly we can write, because for this element cofactor is D, for this element cofactor is A. Yeah, and for other elements it is minus B and minus C, and after taking transport they'll come to their original place. Okay, so that's why we can write it like this. So if I take an example, 1 minus 3, 6 minus 7. Okay, if I take a inverse of it, 1 upon minus 7 plus 18 times minus 7 here, 1 here, 3 will become minus plus 3, minus 3 will become plus 3, 6 will become minus 6. That's all. Okay, so it is, or you can also, so this is 11, you can bring the 11 inside the matrix also. Minus 7 by 11, 3 by 11, minus 6 by 11, 1 by 11, or you can keep it out, your choice. Okay, so yeah, so for 2 cross 2 it is very simple. So let's take a 3 cross 3 matrix. 2 0 1 minus 1 3 2 4 0 5. Process is same. Okay, so A inverse is equal to 1 upon determinant of A adjoint of A. First of all, you have to find the determinant here. Can you tell me the determinant of matrix A? Is 18.
Getting 18, sir.
Yes, correct. So that's all. So let's try to find the adjoint of A here. Adjoint of A means cofactor matrix. Take a transpose of it. Okay. So I'll tell you how to find the cofactor once again. So cofactor for this position is determinant of this. You have to exclude this row and this column. So 3 multiplied by 5 is 15. 15 minus 2 is 15 minus 0 is 15. So multiply by minus 1 raised to the power 2. So it is 15. So similarly, you can write down the rest of the numbers and take transpose of it, you should get this matrix. Okay, and then put these values into this formula and we'll get the inverse out of here. Okay, the process is same, but it will be little time consuming because making an adjoint of matrix A will take like some time, because I've just explained you 15. Let's say what is, so let's call this A1 A2. What is cofactor of A2? Cofactor of A2 is -1 raised to the power 1 plus 2 into, exclude this row and column, -5 minus 8. So it is -13 multiplied by -1, which is 13. And after taking transpose, it will come to this position. Okay, so this is how you have to calculate each and every uh, cofactor and put into this formula. Is it clear? I think we are at the end of the session now. But yeah, before closing this session, I would like to let you know that not from the inverse topic, either they can ask question directly like find the inverse of matrix A and they'll give the matrix, or they can ask questions in some other format also. Okay, so maybe I'll just give you one question and then we'll close the session. Okay, so for example, if A is equal to 1 2 2 2 1 2 2 2 1 and A square minus 4A plus 5 times I equal to 0 is given, find A inverse. Okay, so in this way also they will ask the question. Okay, should be in position to solve it. Okay, can you tell me how you will find the solution for this particular problem?
Multiply that equation by A inverse.
Yes, correct. So it's A square minus 4A plus 5I equal to 0. You can multiply with A inverse on both the sides. A inverse into A square is A minus 4 times I plus 5 times A inverse equal to 0. Okay, so it's A inverse into 0. A inverse into 0 is 0. And from this equation, what we can get is 5 times A inverse equal to 4I minus, sorry, here it's a negative 5I, correct it. So 5 A inverse is equal to 4I or A minus 4I. And this 5 also you can bring it here, 1 upon 5 times A minus 4I. Okay, and then you can put the value of A and I here. A you already know, 1 2 2 2 1 2 2 2 1 minus 4 times I, 1 0 0 0 1 0 0 0 1. Okay, do the subtraction, or this 4 will come here. Basically, do the subtraction, divide with 5, which is 1 upon 5 minus 3 2 2 2 minus 3 2 2 2 minus 3. Okay, that's all. So this kind of questions also you can get from the inverse point of view. Okay, and there is one more type as well, but as we are at the end of the session, I will continue it in the next class. Okay, so in the next class we'll study one other type of problem from the inverse topic, and then we'll start the new topic, which is rank of matrix. Okay, so I'm expecting maybe next class or one more class we will spend on the first chapter. Okay. Okay, do you have any doubt till this? Can we end our session here? Hello? Hello? Okay, yeah. So thank you all for joining this class, and let's meet again on Sunday. I think we have class directly on Sunday, right? Let me just check it. No, we have on Saturday as well. So let's meet on weekends. Thank you. Bye. Have a good night.